today I'll talk about weight measurement just before lunch to make you self-conscious about not eating too much. So this is kind of a side project in my lab just because it was very easy to do with fluidic AFM probes. So there are some issues with it and it can be improved quite a bit, but the initial results I'll show you show that something that anybody with a fluidic AFM can do. So I'll talk about mass measurements in general, and we used beads and hex cells, so there's a typo there. Then we also measured induced pluripotent stem cell cardiomyocytes and look at their mass changes over time. And I'll also suggest some improvements on the device and on the measurement scheme, some of which are already commercialized by NanoSurf. So mass changes are very important and kind of neglected in biology. And they can give you information about the cellular process, about growth, metabolism, proliferation, and so forth. So most existing tools currently use volume as a proxy for biomass. And that is sometimes inaccurate because you're using optical means to detect the volume of the cell, and the cells can have different shapes. So it's good to have a different technique for this. And cell masses range from a few nanograms to picograms, depending on the type of cell and so forth. So how do you measure it? It's a very well-known technique. People use resonance frequency changes of microcantilevers. And there has been a lot of work on this. Manali's group at MIT has developed these microchannel resonators. And also you can functionalize atomic force microscopy cantilevers, so normal cantilevers. And this has been done by, I believe, a Zurich group, which now is being commercialized by NanoSurf. There were preliminary results done in this by Dario in air. And we just try to continue this by using in liquid live cells. So the advantages of using these devices is that the cells can attach to the tip by applying just pressure, so you don't need to functionalize the cantilever. You can also apply positive pressure and just remove the cell and attach another cell. We were able to do multiple measurements. So with one cantilever, you can do within an hour, maybe 7 or 8 measurements quite easily. And the location is fixed, so you don't have to account for the cells migrating elsewhere or attaching some other part of the cantilever. So the setup is, you've seen similar setups before, but here you just apply a small positive pressure so that there won't be anything going into the cantilever while you're approaching your target. And then you apply a negative pressure to attach the target, and then you raise it, you reduce function if you want to, and then you just measure the resonance frequency, and then you just expel the target and you measure the resonance frequency again. And it's a very simple process. And here this was done with metal microspheres in liquids. Obviously, once you move into liquid, the quality factor drops quite a bit. And also the resonance frequency curve measured by the thermal noise method changes, but you still are able to detect and measure masses. You can improve this quite a bit, and we can talk about it later. But we're using this simple equation right now, which is an approximation, so it's still not accurate. You can still improve this because this assumes that you're like, there's no damping and it's a point mass. There are people who have worked on improving this technique, on this kind of type of measurement. And here are just some examples of what we did in liquids. So we use polystyrene microspheres of different diameters. The smallest diameter is equivalent to about, if you use the density of these polystyrene spheres, you can calculate theoretically their mass. And it's about 240 or 80, I think, picograms. So we can easily measure down to that size, and the error is about 100 picograms at this point. So we repeated these measurements with stainless steel microspheres again, and we saw kind of a nice agreement with the estimated value based on the diameter that we measured optically. So there is also an error in estimating the theoretical value. So actually the error for estimating theoretical value is smaller than the variation in the resonance frequency we measure. So similarly, we used hex cells, we trypsinize them lightly, and then we just attach them fluidically. And we're able to measure a number of cells, as you can see, with good agreement with what would be predicted theoretically. So this was already done like a year ago, and we published this. And now I'll talk a little bit about our new data that we haven't published yet. It's not a lot of data, but it just shows that you can take this into a direction that might be quite interesting. So we use the iPSCs, induced pluripotent stem cell cardiomyocytes, which are essentially taken from mature cells like human skin cells and can be specialized into other kind of cells. So this can be used for cell therapy, they can be used for drug testing and investigating aspects of cardiac disease. And I think especially in the area of drug evaluation, they're very useful because you don't have to use animal models anymore. And so eventually I think it will go that way, and also personalized medicine. So understanding also the maturation status of these cells is very important. At the moment, the field has a hard time producing mature cardiomyocytes out of induced pluripotent stem cells. So using mechanical means with an AFM, you can have invaluable insights in addition to whatever people use already. So we use elasticity and mass to provide a way of assessing maturation. So as a side note for NanoSurf here, irrelevant to this, it's very interesting also to look at patch clamping with your system. I think that could also open up doors for drug evaluation. So it's very interesting to go in that direction. At the moment, you know, like patch clamping, this is side note, nothing to do with my talk, but at the moment, like patch clamping is it's hard done. It's very difficult to find specialized people to do it. So like if you can actually combine it with an AFM and automate it, it would be a very useful, I think, machine, especially with your new system. So first we looked at the module of elasticity, and we just looked at day 0 of differentiation, and then at day 141, 145, with a number of cells, and we could see a large difference in the elasticity of the cells. The more mature cells are actually, they have a much higher elasticity modulus. And we can discuss this later, why is that? So we use for all these measurements the NanoSurf AFM that we have in our lab, along with the fluidic AFM. This is done with a conventional cantilever. But now here we use the fluidic AFM to measure the mass of iPSCs at day 0 and at day 173. And you can also see a very big change in mass between the two time points. So to summarize this section, so during differentiation and maturation process, the mechanical properties are changing in the cell, and the cytoskeleton gets organized and so forth. And you have immature cells have less organized cytoskeleton, they have fewer myofibrils and lower stiffness. So as the cells mature, they have more myofibrils and made of actin and myosin proteins, and that contributes to a higher stiffness. So that's what we're seeing. And that has been, you know, people have measured this before, but they have never done it on the same kind of cell line, tracking those cell lines over time. So I also think, like, you know, mass measurements could offer a great promise if you combine it, especially with other techniques that we talked about here, like extracting genomic content and so forth. So now a little bit about improving the devices. We did some simulations. using COMSOL, and we used a specific module for COMSOL. And first, we just wanted to see whether our model is good. So we compared our experimental values with the simulation, and it's quite close. So this reassured us that our model is correct. And then we looked at various aspects. I'm just going to talk about the material here. We found that if you use different materials for cantilevers, such as polymers, while in air, they may not offer such a good mass resolution. In liquid, we noticed that through the simulations that actually outperform the rest. So the key here is that we're looking at the minimum detectable mass. And in this graph, we normalize it with using a silicon cantilever. And by looking at this, we were able to see that there is a 3x improvement in terms of minimum detectable mass using in water, compared to silicon cantilevers, and about 4.5 improvement compared to silicon nitride cantilevers, and also similar to silicon dioxide. So just to summarize my brief talk, so mass and mechanical properties may serve as markers for monitoring differentiation in induced pluripotent stem cells. And we looked and saw a big difference in terms of different time points of day 0 and like actually several days, months later. We need to improve this technique, but this is a non-invasive technique, and I think it has great promise, especially if you combine it with fluidic FM biopsies and so forth. You can do adhesion with it and elasticity. So there's a lot of things you can do with attaching this cell on the cantilever, especially elasticity. You can pick up the cell, measure the mass, and then just push it towards the glass substrate and measure the elasticity of it in one measurement session. So, but the minimum mass, detectable mass, can be improved by cantilever materials and designs, also by adding active vibration. So, so instead of the thermal tuning method that we're using, you can increase the amplitude of oscillation and therefore decrease the minimum detectable mass by using photothermal modulation, basically having 2 lasers on the cantilever, one modulating and moving the cantilever, the other measuring the movement. You can also integrate, which is far more complicated, piezoelectric actuation on the actual cantilever. People have done that with different kind of cantilevers, but not fluidic ones. And then you can also do thermomechanical actuation. And lastly, which can be actually a little bit more easier to do, is magnetic actuation. You just have a coil and just have to have a magnetic material on the cantilever, and you sweep and you can see the frequency changes. So that's my talk, and on future research, we hope to improve this technique so that we can measure finer changes over time during a 2-week initial interval of differentiation, which is far more interesting than what I've shown you so far. So I would like to thank you, and also thank my collaborators. And I've used the Flex AFM from NanoSurf and the CytoSurge nanofluidics, and also a nanosensors probe for this work. Thanks.